Hi, my name is Kirk Marshall. In this module of Network Security Testing with Nmap, we'll be discussing Nmap's phases of operation and presenting some of the basic options that control input and output from the command. We've already seen a simple Nmap command and its screen-based output. Using the default settings is fine for some situations, but it's noisy and kind of like dropping a bomb on the target. If we want to get stealthy or surgical and pinpoint a specific target, we need to gain better control of Nmap through the plethora of options available to us. Using these options, we can graduate from dropping bombs to flying missiles through open windows, down hallways, around corners, and blowing up a single bathroom instead of an entire city block. In this module, we'll start to learn about Nmap's options and the power they provide to us to control Nmap and have it do our bidding. The major phases of Nmap's operation are listed here. We'll be talking about each one of these throughout the course, but in this module we want to focus on target expansion, reverse DNS resolution, port scanning, but only as it pertains to specifying the target ports, and output. As we've already seen, the simplest way to specify a target to Nmap is to give it the IP address of the system we want to scan. With this simplest argument, there is no expansion that Nmap needs to do. Nmap operates directly on the IP address. We can also use the DNS name for the target. Nmap translates the name into an IP address using standard DNS resolution requests. Multiple IP addresses can be combined into one argument using lists. Multiple values for each octet of the IP address can be listed at once by separating the values with commas. In this example, we have two lists. In the third octet, we've specified 54 and 55, and in the fourth octet, we've listed both 1 and 10. All lists are expanded in all combinations, so in this example, Nmap will scan for 4 IP addresses: 192.168.54.1, 192.168.54.10, 192.168.55.1, and 192.168.55.10. Frequently, we want to designate a range of IP addresses, and Nmap allows that using a dash to define ranges. In this example, Nmap will expand the range to 192.168.64.20 up through and including 192.168.64.29, so a total of 10 IP addresses are scanned in this case. When using a range, either side of the range may be omitted, which Nmap will interpret to be either the minimum or maximum value possible. So specifying 172.16.-4.1 will expand the third octet to include 0, 1, 2, 3, and 4. Here we have one last range example where the second octet is just a dash alone. In this case, Nmap will expand the second octet to be all possible values ranging from 0 through 255. Nmap can also handle classless interdomain routing or CIDR address specifications. IP addresses are described as consisting of two groups of bits, with the bits on the left defining the network address and the bits on the right defining the host identifier. The number after the slash in a CIDR notation indicates the division between the network address and the host identifier and is interpreted as being the number of bits starting with the leftmost bit that makes up the network address. In this case, 29 bits define the network and 3 bits define the hosts on the network. Nmap expands this CIDR notation into a list of 8 IP addresses. Most of the target specification types can be combined. Here are several target lists, all of which are valid. Note that the targets are space separated. In the first example, we're combining an IP address with a DNS name. In the second example, we're using both ranges and lists. And in the last example, we're specifying a small network using CIDR notation and 3 DNS names. Of course, more complex combinations are possible, but I'll let you get creative with those on your own. If you're building a list of target specifications and you're curious to see if it's going to do what you think, you can verify your specification with the dash lowercase s, uppercase L scan type, which tells Nmap to perform its target expansion phase and to exit before actually scanning the target systems. So if I execute the command nmap-sl 192.168.1.56/29, the output will look like this. As you can see, Nmap did not try to determine if the hosts were up or perform any port scanning. It simply lists the expanded IP addresses and exits. Passing a large list of targets to Nmap on the command line can be cumbersome. To get around that, Nmap allows for targets to be stored in a standard text file and then passed to Nmap using the -i_L option. Entries in the file can be in any of the same formats we've already discussed and can be separated by one or more spaces, tabs, or new lines. After expanding the target list into individual IP addresses, Nmap performs the host enumeration phase to determine which IP addresses are actually associated with live systems. Once Nmap has that list, the next phase of operation is a reverse DNS lookup on the IP address, trying to turn it into a name. Here we've provided Nmap with the host name www.ibm.com, which during the target expansion phase was turned into an IP address of 23.4.152.139. During the reverse DNS lookup phase, that IP address is turned back into a host name, resulting in the name a23-4-152-139.deploy.static.akamitechnologies.com. In this case, the forward and reverse DN entries don't match. Performing reverse DNS resolution isn't always desirable, especially since it can be slow, so Nmap allows disabling it by specifying the -n flag. There are also times when you want reverse DNS resolution for all IP addresses, not just the live systems. Including the -R flag will enable reverse DNS resolution for every target IP address. Port scanning is Nmap's core operation. We're going to save the full discussion of the port scanning phase until the module on TCP and UDP scanning. Right now, we want to discuss the portion of the port scanning phase that deals with port specification and how Nmap expands our port specification into a list of ports. As you'll see, it's very similar to the target expansion mechanism we've already discussed. There are two methods of port specification, either explicitly using the -p flag or by reference using the data stored in the nmap-services file. Let's start by discussing the -p flag. The simplest way to designate a port is with a single target port. We can also provide a list of target ports. Each of the values in the list are separated by commas, and since the list must be passed through the shell as one argument, there must be no spaces in the list. Target ports can also be defined in a range of ports. Here the range 135-139 will be expanded to 135, 136, 137, 138, and 139. The default values for the lower limit of the range is 1, and the default for the upper end is 65,535. Either or both of the range endpoints may be left unspecified, for which the default value is assumed. So a range specification of -1024 is expanded to 1 through 1024. And a dash all by itself is expanded to 1 through 65,535, or all possible port number values. Lastly, port specifications can include the desired protocol. Usually Nmap performs either TCP or UDP scanning, but not both. If we want to mix and match ports and protocols, we can include the protocol designation with each port number list or range. Okay, let's talk about the nmap-services file for a few minutes. The nmap-services file is a configuration file distributed with Nmap that mimics the standard Unix/etc/services file. The services file is a table listing service names like FTP or SSH in column 1 and the associated port numbers in column 2. There are several notable differences between the system file and the one distributed with Nmap. First off, the nmap-services file is a much more complete list of services. For example, the /etc/services file on my Linux system has 608 entries, while the nmap-services file has almost 20,000. Secondly, the nmap-services file includes a frequency field, which isn't included with the /etc/services file. We'll talk more about the frequency in just a moment, but the published value is an estimate of how likely it is that that port will be found open. Basically, the bigger the frequency number, the more popular the port is. So the simplest way to use the information in the nmap-services file is to specify a service by name. Nmap uses the services file to look up the port number and scan the designated port by number. Name services can also be scanned using a partial name and a wildcard, such as an asterisk, to scan all services that match the wildcarded string. For example, HTTP asterisk will expand to this list of HTTP services. Valid wildcards are the question mark, which matches a single character, and the asterisk, which matches 0 or more characters. The --top ports flag allows you to specify a count of the top most frequently used ports. For example, specifying a count of 5, the TCP ports that would be scanned are HTTP, Telnet, HTTPS, FTP, and SSH. The ports are selected based on the values in the frequency column of the nmap-services file. Lastly, ports can be specified by referring directly to the frequency value stored in the nmap-services file using the --port-ratio flag. The frequency supplied is constrained to be a value between 0.0 and 1.0, but practically, the values should be less than 0.2 if you really want to scan anything. As you can see from this sorted excerpt from the nmap-services file, the highest frequency listed is 0.48 for HTTP. Furthermore, the frequency values fall off dramatically to less than half that for the 10th most frequently used service, DHCPS. It should also be noted that most of these high-frequency services are UDP-based, with the only TCP service being HTTP at number 1. As we've demonstrated, you don't have to specify any port specifications at all, and Nmap will still scan something. So what's the default? By default, Nmap scans the top 1000 TCP ports. Of course, most of these port specifications can be combined. Here are 3 valid examples. In the first example, we're combining port number lists with port number ranges. The second example combines nmap-services named services with wildcards and numbered ports. And the last example combines protocol specifications with lists and ranges. All of the scanning Nmap performs is worthless if we can't get meaningful, easy-to-read results as output. We've seen several examples of the interactive or screen output from the command. Nmap always provides this output, even if we ask that it redirect the results to a file. Even though Nmap is fast and efficient, some scans will still take a while to complete, and at times, the interactive output is frustratingly quiet. If you're curious about what, if anything, Nmap is doing, you can press Enter at any time while the command is running, and Nmap will print 2 status lines giving you an idea about its progress through the scan's various phases, and how much longer it might take to complete the current set of scans. In this example, you can see that Nmap is currently performing the ping scan, which it expects to complete in about 21 seconds. Remember that the ping scan is followed by several other phases, including the possibly lengthy port scan. Since the statistics displayed are only for the current operational phase, the complete scan might take considerably longer than the estimate shown, but still, it's reassuring to know that the process hasn't hung and that it will someday finish. Sometimes you'd like to know why Nmap has classified a port as either open or closed. The "reason" option alters the output with a 4th column that includes the result that caused Nmap to deduce the results it's displaying. In this example, we can see that Nmap classified port 80 as open because it received a SYNAC packet in response to its probe and a connection refused response to its connection request on port 443. We'll talk more about these reasons and what they mean in the next module. We've already seen output that includes the open and closed states for a port, but Nmap will also tell us if the port was filtered or unfiltered and can even classify a port in combinations of these states. All of that is informative and useful at times, but frequently all we care about are open services. The "open" option instructs Nmap to only display ports in an open state. Seeing the results on the screen is nice, but more often than not, we'd like to save the results to a file. The "O" option enables saving the results in different file formats. The capital N argument to the option saves the data in normal format, which is very similar to the interactive screen output. The capital X argument saves the data in XML format, and the capital G argument saves the output to a file with all the information for each host on a single line, which facilitates parsing the data with a search tool like the Unix grep command. All of these options are called using the same syntax and require a file name where the data will be stored. In summary, we've discussed several of Nmap's phases of operation and learned how Nmap expands the target and port specifications we provide on the command line to an actual list of targets. Armed with just these options, we can perform a variety of scans and gain valuable insight into the operation of our networks, but we still have several gaps in our knowledge. Join me in the next module as we begin to fill these gaps on our way to becoming Nmap ninjas. Hi, my name is Kirk Marshall. In this module of Network Security Testing with Nmap, we'll be discussing host enumeration and network mapping. These two phases are highlighted here on the list of Nmap phases of operation that we presented in the previous module. We'll be spending the bulk of this module talking about host enumeration, which is one of Nmap's key processes. We'll also talk about network mapping, or traceroute, which we're taking a bit out of order since it seems to fit better here from a subject matter perspective. Recall that we said that to identify hosts on a network, Nmap sends specially crafted packets to the target host and then analyzes the responses it receives back. The queries are designed to elicit a response from the target system that Nmap can use to deduce information about the target. The objective of the probes during the host enumeration phase is to get a response, any response, back from the target which might indicate that there is a live system at that IP address. To understand Nmap's functionality, we need to delve into the construction and contents of these packets. All network packets are constructed as a series of nested envelopes, or like a stack of Russian dolls. According to the OSI model, the outermost envelopes are the physical and data link layers. Next comes the network and transport layers, and finally, the session, presentation, and application layers. Nmap operates at the network and transport layers, so we'll be focusing our discussion on just those two layers. If you're interested in learning more about the other layers, Wikipedia is a good place to start. The envelope at each layer has a header which contains addresses and other information pertinent to the handling and delivery of the packet at that layer, and then the contents of the packet, which to that layer is just data. Likewise, each nested envelope has its own header and data sections. Let's discuss the network and transport layers. The network layer is responsible for the movement or routing of packets across the network. On the Internet protocol is the protocol in use at the network layer. The header for an IP packet is laid out like this. Each line represents 4 bytes of data, so the IP header is a minimum of 20 bytes long. The fields of importance to Nmap are the flags and fragment offset fields and the source and destination IP addresses. We'll be discussing the 2 flags, which pertain to fragmentation, and the fragment offset field later in the course when we talk about firewall evasion techniques. The source IP address is most often the IP address of the local interface from which we're sending the packets, but can be set by Nmap to other values too. The destination IP address is, of course, simply the target. The transport layer provides the flow of data between 2 applications on 2 hosts across a network. There are 3 transport layer protocols which are of importance to Nmap. The Internet Control Message Protocol, or ICMP, the User Datagram Protocol, or UDP, and the Transmission Control Protocol, or TCP. We'll discuss each of these in turn. As we just mentioned, the TCP layer controls the flow of data between hosts, but that's not the function of ICMP. ICMP is used to pass messages from one system to another or perform network diagnostics. In that sense, it really is more part of the IP layer. However, it functions at the TCP layer, so we're discussing it here. ICMP headers are 8 bytes in length. The 2 header fields which we need to understand are the type and code fields. ICMP messages are one of 2 primary types. They are either a request and response pair or a one-way communication. usually about an error of one type or another. The type field designates the major category of the message, while the code field further defines and clarifies the message. There are three request and response pairs: echo, timestamp, and address mask. If a querying host sends an echo request to a destination, the destination host is supposed to send the matching response. So if Nmap sends a timestamp request to a target system using type 13 and code 0, the target should respond back with a timestamp reply with a type 14 and a code 0. We're going to be discussing several of these request and response dialogues throughout the remainder of this course, so let's introduce this timeline with this simple example to help with more complex examples that will come later. Here we have the same components in the previous diagram: the testing laptop and the target server. The upper and lower lines represent each system, and time progresses from left to right. So using the same timestamp example, our timeline would look like this. The testing system sends the timestamp request using type 13 and code 0 to the target, which replies with a timestamp reply using type 14 and code 0. Each of these request and reply pairs can be invoked using the listed Nmap flags. Receiving a reply to one of these three request and response pairs tells Nmap that there is indeed a live host at the target IP address. By default, Nmap sends both an echo request and a timestamp request to the target. If the target system responds to any of these requests, it provides a firm confirmation that a system exists with the target IP address, and Nmap reports that IP address as up. The other type of an ICMP packet is the one-way communication of a message, usually an error. The primary type we're interested in is type 3, which indicates destination unreachable. Destination unreachable is quite broad and could mean many different things, so the code field is used to further describe the error and indicate the specific reason that it was unreachable. Some of the more frequent codes, ones that we'll be referring to later, are listed here. Code 3, for example, indicates that the port we tried to connect with on the target system is unreachable, which means that there is no running application associated with that port. These types of error messages are usually sent by the target system or an intervening router back to the testing system in response to either a UDP or TCP probe packet. If the error is returned from the testing system, Nmap reports the system is up. The Transmission Control Protocol is one of the core protocols on the Internet which provides a reliable, ordered, and error-checked stream of bytes between applications running on computers across a network. If UDP is like a letter passing through the postal service, TCP is like a phone call. When I want to talk with someone on the phone, I dial their number and their phone rings. When they pick up the phone, they say hello. Then I confirm my presence by saying hi. At this point, I've established a connection between myself and the other person, and the dialogue starts. I might say, "This is Kirk," to which they might reply, "Hi, Kirk." Then I'd launch in with, "I'm calling because blah, blah, blah," until the conversation ends, and we'd both say goodbye. Using a similar protocol, TCP provides the means of establishing a connection and provides for the ongoing bidirectional transfer of data between two endpoints. A TCP header, which is comprised of 20 bytes of data, looks like this. The fields of importance to Nmap are the source and destination ports, sequence number, acknowledgement number, and flags. The source and destination ports function identically to the source and destination ports in UDP and need no further discussion. The sequence number is a count of the bytes exchanged by the two endpoints. The receiving system, which may receive bytes from the data stream out of order, uses the sequence number to reassemble the data packets back into the correct order. The receiving system uses the acknowledgement number to confirm back to the sending system which packets have been received. The flags or control bits are used to indicate the type of packet or call attention to other significant conditions. The flags that we need to be familiar with are the urgent, acknowledgement, push, reset, synchronize, and finish flags. Rather than define them now, I'll wait and let the context of our first use define them. They'll make more sense then anyway. Since this probably makes little sense from just the definitions, let's walk through a connection sequence to help clarify these fields and increase our understanding of the protocol. A client initiates a TCP session by sending a packet to a server with the SYN flag set. The SYN flag indicates to the server that the client is attempting to establish a session and that the sequence number set in the packet should be used as the initial sequence number for the data stream originating at the client and going to the server. The server responds with a packet that has both the ACK and SYN flags set. The ACK, or acknowledgement flag, indicates that the value of the acknowledgement number is significant in that it acknowledges and confirms the initial sequence number set by the client. The SYN flag indicates that the sequence number in the packet should be used as the initial sequence number for data originating at the server and flowing to the client. The client responds with a packet with the ACK flag set, which acknowledges the server's initial sequence number. These three packets, collectively called the TCP three-way handshake, serve to establish a connection between the client and the server. Both systems are now set to sequence and track the data packets from the other system. We're ready to begin passing data. Data can now flow freely between the client and the server. The sequence numbers and acknowledgement numbers are incremented and confirmed with each passing packet, until we have no more data to pass. When either system is ready to terminate the connection, it sends a packet with the FIN flag set. The receiving system acknowledges the FIN with an ACK and then sends a FIN packet of its own. The final packet of the session is one last acknowledgement, and the session is done. Nmap has two options for performing host enumeration using TCP packets, the -PS and the -PA options. Both of these options operate on port 80 by default, but other ports, lists, or ranges may be specified. Notice there's no space between the option and the port specification. On a Unix system, only the root user is able to send and receive raw TCP packets, which are used by these options. If you execute them as a non-root user, Nmap will enable a workaround, so you will get some results, but these options are best executed as root. The following discussion assumes root privileges. The -PS option sends a TCP packet with the SYN flag set, just as if we were trying to initiate a connection. For the purposes of host enumeration, one of two conditions are possible. Either the port is open or the port is closed. Finding that the target port is open is rare, but when it does occur, the target will respond to our SYN packet with the standard SYN-ACK reply. This confirms to Nmap that a system exists at that IP address, and therefore Nmap has no further need of communicating with the target system. And so instead of completing the three-way handshake with the final ACK, Nmap sends a packet with the reset flag set, which tells the remote system to tear down the connection and terminate communications. This type of connection, where we abort the session after the first SYN-ACK reply, is often referred to as half-open scanning. The network and transport layer headers for a TCP probe packet look like this. The source IP address is set to the IP address of the testing system, which in this case is 192.168.53.35, and the destination IP address is set to that of the target, 192.168.53.201. The source port is set to an ephemeral port, in this case 7233, while the destination port is set to the target port number of 80. The sequence number is set to a random number, and the SYN flag is on. If the target part is open, the reply will look like this. The source and destination IP address and port numbers have been swapped. The acknowledgement number is set to the incremented sequence number from the original probe, and both the SYN and the ACK flags are set. This is the second packet in the standard three-way handshake. The other possibility is that the port is closed, which is common. In this case, the remote system doesn't reply with the standard SYN-ACK packet. Instead, it replies with a reset packet, indicating that communication with that port is not possible and that the connection attempt should be aborted. Notice this is different from UDP. Scanning a closed UDP port results in an ICMP port unreachable message. With TCP, the error is handled within the protocol with the reset flag. In both port open and port closed situations, we receive a packet wherein the target's IP address is in the source address field of the IP header, which positively confirms the existence of a live host at the target IP address, so Nmap reports the system as up. Scanning a closed port, the response will look identical to the port open response, except the reset flag will be set instead of the SYN and ACK flags. The -PA option sends a packet with the ACK flag set as if we were in the middle of a communication session with the target. This packet is spoofing an acknowledgement to data that never existed. The remote system is of course going to have no record of needing an acknowledgement and responds to the testing system with a reset packet, asking that the client's fictitious session be discontinued. This response is exactly what Nmap is trying to elicit, since it confirms the existence of a system at that target IP address. This probing method purposefully deviates from the standard packet sequence defined by the TCP protocol in an effort to deceive and evade filtering devices. We'll come back to this subject and talk more about firewall evasion in a later module. Occasionally, it is desirable to disable host enumeration and have Nmap run a port scan on every IP address you provide. The -P lowercase n option disables host enumeration completely. Here's an example of Nmap using all the host enumeration options we've discussed in this module. The first three options, -PE, -PP, and -PM, all send ICMP request probes. The -PU option sends a UDP probe, and the -PS and -PA options send TCP probes. As an example, the results are a bit boring, since the only output is the brief message, "Host is up," but from a network auditing perspective, that simple message is extremely valuable. Okay, let's move on and talk about network mapping using traceroute. The traceroute capabilities of Nmap are similar to those available using the Unix command line tool of the same name. In both implementations, traceroute sends specially crafted packets over a network in an attempt to discover the network path between two systems. The advantages of using Nmap are that the functionality is built directly into Nmap and that its probing is performed in reverse order. Here we have two geographically separate systems, our testing system in Phoenix and the target in Tampa. Using traceroute, we can discover the intervening network topology, which might look like this. In this simple example, traceroute has identified 3 routers and 2 networks that were previously hidden from us. We of course already knew about the local and remote networks. Traceroute works by manipulating the time to live field in the IP header. The time to live, or hop count, is a mechanism that limits the lifespan of a packet and prevents data from remaining on a network indefinitely. When a packet is built and sent onto the network, the sending system sets the time to live to some finite value. For this simplistic analysis, we've set the time to live to 3. In any real network, the time to live would default to a more realistic value, perhaps 64. Routing rules require that each router decrement the time to live value before passing the packet on, and that when a packet with a hop count of 0 or 1 is encountered, it must be discarded and the originating system be notified using an ICMP time exceeded message. The Unix traceroute command starts with a time to live of 1 and increments the value with each successive packet. Nmap's traceroute is unique in that it starts with a large time to live and decrements the value down to 1. By working down through appropriate time to live values, Nmap can employ clever caching algorithms to speed up a trace and send fewer packets. Like standard traceroute, Nmap can use ICMP, UDP, or TCP probes, but the choice of which type is used is dependent on the type of scan being performed and is not directly user selectable. Traceroute is enabled using the --traceroute option. In this command, we've also specified that we only want to scan port 80, and the -n option turns off DNS name resolution. From the output, we can see that Nmap performs the host enumeration phase and tells us that the target system is up or live. Then it moves on and performs the port scan phase and prints the output telling us that port 80 is closed. After completing the port scan, it performs the traceroute phase, in this case using TCP port 80. The output shows us the discovered list of routers to the target system. The hop column displays the time to live. The RTT column lists the round trip time for the packet in milliseconds, and the address is of course the IP address of the router. The ellipsis at hop 3 indicates that no response was received from the probes with that time to live value. In this module, we've presented the host enumeration and network mapping phases of Nmap's operation. Using these two phases, the network security tester can discover the topology of the networks under review and identify live systems on those networks. All of Nmap's port scanning options are enabled using the -s option and an uppercase letter argument designating the type of scan desired. We'll be discussing 7 of these scan types. The first one, capital U, specifies that a UDP scan should be performed. The rest of them all specify different types of TCP scans. We'll discuss each of these options in turn. Once a scan type is specified, Nmap sends appropriately constructed probes to the target and listens for the replies. One of 4 results might occur. A reply packet might be received from the application running on the target port, from which we can conclude that the target port is open. We could receive an ICMP port unreachable error or reset packet, which indicates that the port is closed. We could receive an ICMP error message from an intervening router, which indicates that communication with the system or port is prohibited or filtered. Or lastly, we could hear nothing back. For each of these scan types, we'll investigate each of these 4 results. Let's start with UDP port scanning. UDP port scanning is enabled using the -s capital U option as shown in this command. Open UDP ports are only detected when the associated application provides a reply. Probes sent to UDP ports that commonly provide replies, such as DNS on port 53 or SNMP on port 161, contain a payload designed to elicit a response from the target application. Probes to other UDP ports have an empty payload. Closed ports are easily detected when an ICMP port unreachable response is received. These ICMP error messages are sourced from the target system. ICMP error messages from an intervening router or firewall indicate that we are prohibited from reaching the destination system. These errors are not sourced from the target and are classified by Nmap as filtered. Some of the ICMP errors that Nmap might receive are listed here. Again, these errors are generated from an intervening router and not by the target, so the receipt of one of these messages doesn't tell us anything definite about the target other than we're not allowed to communicate with it in one way or another. Lastly, a probe might not ever receive a reply. Nmap will time out waiting for a response and resend the probe, but eventually it will give up. There are at least 2 explanations for not receiving a response. One is that an intervening router or firewall has silently dropped the probe. The other is that it could also be an open UDP port under normal operations. Many UDP services run as listening services and accept incoming packets and never or rarely provide a response. Syslog is one example of such a service. It will happily accept incoming log entries, but never provide a reply or confirmation of receipt. Because of these 2 possibilities, if Nmap never receives a response, it can't determine if the port is open or filtered, so it reports both. These results are summarized here in this table. We'll add to it as we look at each scan type so we can compare the results of each method. Let's execute a couple commands and look at the output. In this command, I'm asking Nmap to perform a UDP scan on port 53 of 192.168.0.1. The results show that the domain service on UDP port 53 is open and accepting connections. The reason Nmap provides indicates that an application response was received to the query included with the probe. Let's take a look at another example. This command is probing the ISACAMP service on my cell phone. ISACAMP is used to exchange cryptographic keys, usually as a precursor to establishing a VPN tunnel. I'm expecting this port to be closed. Sure enough, Nmap found the port closed and reported the reason as port unreachable, indicating that an ICMP Type 3, Code 3 message was received. The rest of these options all specify types of TCP scans. Let's start our discussion with the Connect scan, which is enabled using the -s T option. With a connect scan, Nmap attempts to perform the complete three-way handshake. If the connection is established, Nmap terminates the connection with a reset packet. These sessions are established using the operating system's network packet construction routines and can therefore be executed by non-root users. Open ports are positively determined since a SYN-ACK packet is returned from the application running on that port on the target system. Closed ports are also positively determined since a reset packet is returned from the operating system on the target system. As with UDP, ICMP error messages sourced from intervening routers are classified as filtered, and if no response is received, Nmap also reports the port as filtered. Here's our updated response table. Note that with the TCP connect scan, we received a reset packet from the application rather than an ICMP port unreachable, as with UDP. Also, notice the difference in classification for no response. With UDP, there's some ambiguity between open and filtered. That's not the case with TCP. All right, let's do another quick demo. In this command, we're requesting that Nmap perform a TCP connect scan against port 80 and 81 on the default router for my office network. As you can see, Nmap received a SYN-ACK from port 80 and therefore lists the port as open. A reset packet is returned for port 81 and Nmap lists it as closed. Since Nmap is relying on the operating system's network packet construction routines for connect scans, it also relies on them for errors. In this case, Nmap gives the reason as reported by the operating system, which is connection refused. The S argument defines half-open scanning and is enabled using the -s capital S option. The capital S argument specifies a TCP half-open scan. For each port scanned, Nmap begins a normal three-way handshake, but after the initial SYN-ACK response, the connection is terminated with a reset packet. Packets for these sessions are built using Nmap's internal packet construction routines and therefore require root privileges. This is the default scan type if performed as root, since it is the fastest and uses minimal resources on both the scanning system and the target. If you attempt to execute the scan as a non-root user, Nmap barks at you and aborts. The results of a half-open scan are identical to a connect scan. Again, open ports are positively determined since a SYN-ACK packet is returned from the application. Closed ports are also positively determined since a reset packet is returned from the operating system on the target. ICMP error messages are interpreted as filtered, and if no response is received, the port is also classified as filtered. The results from the half-open scan are identical to the connect scan. Between the two options, it's best to perform the half-open scan unless you're scanning as a non-root user. All right, let's look at the results of a half-open scan. In this example, we're duplicating the command from the connect scan type and have only changed it to perform half-open scans using the capital S argument. The only difference in the output is the reason supplied for port 81, which is closed. Since Nmap performed the scan using its own internal packet construction routines, it is able to provide an exact reason for the closed classification, which in this case is due to a reset packet. These three scan types are very similar, so let's discuss them together. TCP null, FIN, and EXMA scans are enabled with the capital N, capital F, and capital X options as shown here. These scans use specific flag settings in the TCP header when constructing the probes. Here's the TCP header again. The null scan sends a packet with no flag set. The FIN scan sets the finish flag, and the EXMA sets the urgent, push, and finish flags, lighting the packet up like a Christmas tree, hence the name. Other flag combinations that produce identical responses are possible, but the important point is that the SYN, ACK, and reset flags must not be set. The reason is that during a normal TCP conversation, there should never be a packet that doesn't have at least one of the SYN, ACK, or reset flags set. It just shouldn't happen. The RFC describing TCP communications states that if a system receives a packet without the SYN, ACK, or reset bits set, it should drop the packet. What this means for interpreting our scan results is that using any of these three options, N, F, or X, You'll never be able to positively determine if a port is open, since the target should drop the packet and you'll never get a response. This result is the same ambiguity with UDP scanning. No response could mean either that the port is open or filtered, but we can't determine which. In both cases, Nmap reports the port as open/filtered. Closed ports respond with a reset packet. If an ICMP error message is returned from an intervening router, Nmap classifies the port as filtered. Here's our updated table. Because the N, F, and X scans will never identify an open port, they are of limited usefulness. A few situations where they might be of use are when working through packet filtering firewalls and attempting to avoid IDS detection. Even so, they should be used as a last resort. Let's do a quick demo of a fin scan. Here we're scanning the same ports on the default router for my network using a fin scan. The results show that a response was never received to our probes on port 80, since the proper handling of a fin packet that's not part of an ongoing conversation is to drop it. Nmap can't distinguish between open and filtered ports, so it reports both. A reset packet was received for port 81, clearly indicating that it's closed. Finally, let's talk about ACK scanning. TCP acknowledgement scanning is enabled using the -s option. Like with the ACK host enumeration technique presented earlier, the ACK port scanning option sends an acknowledgement to non-existent data. When scanning both open and closed ports, the target system will always return a reset packet, so Nmap labels them as unfiltered, meaning that they are reachable by the ACK packet, but whether they are open or closed is undetermined. Again, if an ICMP error message is returned from an intervening router, Nmap classifies the port as filtered. And as with other scan types, non-responsive probes are followed up with repeat queries, and ports that don't respond are labeled as filtered. The ACK scan is great for mapping out firewall rules. If we can reach the target system to either open or closed ports, we know that a firewall allows that traffic. If we can't reach the port, it is assumed that a firewall rule is blocking or filtering the traffic. We'll come back to this subject in our discussion of firewall and IDS evasion techniques. Let's look at some output from an ACK scan. Here we're scanning ports 20 through 25, and port 80 and 443 on 192.171.229.13. Since an ACK scan receives identical responses from both open and closed ports, we can't tell the difference. These ports are reported in the output as unfiltered, and the reason given is that Nmap received a reset packet. Other ports are listed as filtered. These results don't tell us as much information as we'd like to get back about the target, but they do reveal the configuration of any filtering devices between us and the target. In this case, we can surmise that a firewall is blocking access to ports 22, 25, and 80. In the previous module, we mentioned that Nmap will send out repeat probes trying to elicit a response from a target port. The --max-retries option controls how many probes will be sent before giving up. The default number of retransmissions isn't well documented, since in one section of the manual I found it stated as 10 retries, and in another section of the manual it says 6. In trying to determine which was the correct value, my testing found that only 2 retries are sent. It's kind of confusing. Anyway, if you need or want to ensure a specific number of retries, it's probably best to set the value explicitly using this option. When Nmap begins the scan of a system, it doesn't know whether the target is next door or halfway around the world. It errs on the side of caution and sets a conservative initial timeout value for how long it will wait for a return packet before retransmitting. By conservative, we mean long. How long is controlled by the --initial-RTT-timeout argument. If or when a target responds, Nmap notes the round-trip time for the conversation and adjusts the wait time accordingly. If we know our target is next door, we can set the initial RTT timeout to a lower value to speed up the startup time of the scan. In addition to the initial timeout value, we can also set a minimum and maximum value for the timeout. Internally, Nmap maintains a running timeout value for determining how long it will wait. These two options set a minimum and a maximum value for that internal timeout. The --host -timeout option allows you to define the maximum amount of time you are willing to wait for Nmap to completely scan any one host. A host that times out is completely skipped, and no report entry is generated for it. Nmap pauses briefly after sending a probe before sending the next one. It does this to prevent flooding the network and losing packets for which it will have to retransmit. How long Nmap pauses is controlled through these two options. Nmap scans a group of hosts in parallel and uses these two host group settings to control the size of the groups. One place where you can see the effect of these options is in Nmap's screen output. When scanning a large group of targets, you'll see a bunch of results spew across your screen in one big chunk and then nothing for a minute or two, then another big chunk of data and then nothing. This repeats until the scan is complete. Nmap is scanning targets in the defined host group size and displaying the results as each host group completes. These options control the size of the data chunks. Ports are also scanned in parallel. These two options control the total number of probes that may be outstanding for a host group. The --min-rate and --max-rate options control the rate at which packets are sent out. The rate is defined in packets per second. So I've discussed these options as a pretext for providing a glimpse into Nmap's internal operations. Like the idea of scanning parallel groups of hosts, which are important for understanding Nmap and being able to tailor it to our needs. However, most of the time you probably won't need to alter Nmap's default functionality. Internally, Nmap maintains a number of variables that track and control its performance and ensure a reasonable level of accuracy. These variables allow Nmap to speed up or slow down automatically in an attempt to balance these two antipodian goals. Rather than set each of these options individually, Nmap provides 6 performance templates that allow them to be controlled as a group, which is far more convenient. The 6 templates in order from super slow to crazy fast are paranoid, sneaky, polite, normal, aggressive, and insane. Here are 2 examples of using the templates in a command. The argument to the -t option can be specified as either the number or as a word. The word, polite in this case, is case insensitive. The Nmap documentation states that the default template is T3, which sets the variables like this, and T5, which is insane, sets these values. T3 is recommended for over-the-internet scans, while T4 is recommended for internal scans. While you might be tempted to use T2 or polite setting, be aware that it can cause the scan to take 10 times longer than the default T3. Also be aware that the super slow setting T0 or paranoid sets the --scan-delay option to 5 minutes and disables parallelization. This equates to sending out 1 packet every 5 minutes. That truly is paranoid and could take a very, very long time to complete a scan. There are 3 technologies that can provide frustration for our scanning efforts: firewalls, network address translation, and intrusion detection systems. All 3 of these are pervasive in today's environment, and you can't swing a Cat5 cable before you run into at least one of them. We'll discuss each and how they can affect your results. Let's start our discussion with firewalls. A firewall is a network security system that controls network traffic passing between 2 networks based on a configured rule set. It establishes a barrier between a trusted, secure internal network and another network, for example the internet, that is assumed to be insecure and untrusted. The firewall looks at packets traveling from one network to the other and either allows or denies the forwarding of the packet based on the contents of the packet headers, or sometimes the packet payload. Decisions are primarily made based on the socket, which is the source IP address and port number, and the destination IP address and port. Other values from the header can also be used to make decisions, most notably the flags from the TCP header. There are three primary types of firewalls: stateless packet filters, stateful packet filters, and application or proxy firewalls. We'll discuss each of these architectures and how they react to port scanning. Of course, we only need to discuss how firewalls handle packets directed to open ports, because closed ports are closed, right? It doesn't matter what we send to a closed port, it's going to get dropped. Before we go any further, let's discuss connect and half-open scanning now. Since both of these scan types utilize standard TCP packet streams, all firewall types react according to their rule sets. That is, if a target port is allowed by the firewall rules, the traffic is passed through. There's nothing unusual with these scan types. We'll discuss the other scan types and how they are handled by the three firewall types in the subsequent discussion. A stateless firewall is one that looks at the socket defined in every inbound packet and compares it to a list of allow and deny rules. Based on the socket and the rules, the firewall either rejects or forwards the packet on to its destination. The architecture is like that of a filtering router in that the same packet headers that flow in one side flow out the other. Packets are filtered based on information in the packet itself and have no record of prior transactions. A typical rule set might define that any inbound packets to port 80 on IP address 10.23.156.8 should be allowed, and any outbound packets from port 80 on that same IP address should also be allowed. Other rules might deny traffic on port 3306 or several other ports. Okay, let's talk about how a stateless firewall reacts to NFX and ACK port scanning. Rules are generally written to filter by port, and stateless firewalls don't inspect the TCP flags, so if our target port is open, these probes will pass through and will receive a reply in return. This should be the case for all of these scan types. As we mentioned earlier, the ACK scan will return a reset from either an open or closed port, making the results for the target system ambiguous. However, scanning ports blocked by the firewall will result in no response since the packets will be dropped. These two sets of results allow us to determine which ports are open through the firewall and which ones are closed, thus mapping the rules. Stateful firewalls look at inbound packets and base their pass-drop decisions on either their state table or on rules that describe the allowed flags in the TCP header. Rule sets for stateful firewalls typically define allowed connections based on the TCP SYN flag that starts the three-way connection. If a rule exists that allows the establishment of a connection over the targeted port, an entry is placed in the state table, indicating an approved connection. The state table is basically a list of approved and established sockets. Subsequent packets that arrive using the same socket are passed through the firewall based on the contents of the state table alone. The advantage of a stateful firewall is that looking up sockets is far faster than looking through the rule set. Let's look at what happens when a stateful firewall is subject to an NFX scan. Recall that all these flag combinations are essentially illegal since they don't have at least one of the SYN, ACK, or reset bits set, and the RFCs state that they should be dropped. A stateful firewall should inspect the flags and drop the packet accordingly. Furthermore, since the packet doesn't have a SYN flag set and the conversation isn't in the state table, the packet should also be dropped. Recall that an ACK scan sends probes as if they were coming from the middle of a conversation with no preceding three-way handshake. In this case, the firewall is going to see the packet with the ACK flag and attempt to look up the socket in the state table, which it won't find, so the firewall should drop the packet. Application firewalls are different from both a stateless and stateful firewall in that they don't just route packets from one network to another. An application or proxy firewall presents a separate TCP/IP stack on either side of the device. Packets flowing into the device on one interface are completely unpacked down to the application layer data. The contents, if there are any, are interpreted as according to the protocol of the target application and then moved over to the other interface, where the firewall then builds a completely new set of headers on the outbound interface before sending it out. Application firewalls are specific or must have a specific module for each application protocol they wish to support. If they don't have an appropriate module to interpret the application data, they typically fall back to performing as a stateful inspection firewall. So how will an application firewall react to NFX scans? Since the packets on either side of the firewall are completely independent, any shenanigans we try and pull with invalid flags on the outside of the firewall are not going to be sent to the target. The firewall will see them and most likely drop them. Even if they are forwarded, which is unlikely, the firewall will use valid header data when building the packet on the far side of the firewall. In a similar manner, ACK scans will arrive at the firewall, and since they're not part of any valid established connection, the firewall will drop the packet. In the unlikely event that a reset is returned, it will be from the firewall and not from the target system. No matter the architecture, most firewalls have a default deny policy, meaning that at the bottom of the list of rules is a catch-all that says, if you get here, drop the packet. Another thing to be aware of is that many firewalls implement limits on packet rates. For example, when performing UDP port scanning, the target system may generate thousands of ICMP port unreachable messages. Many firewalls limit such responses to a small number per second. This type of response profile can seriously impact the speed at which a scan will complete. Detecting when you're up against a firewall isn't always easy or even possible. Some clues that can help you deduce that you've encountered a firewall are available using the previously mentioned traceroute and -O options. Another option that isn't always effective but can help is the --bad sum option, which is called like this. This option causes Nmap to create a bad checksum in the TCP header. All host IP stacks should drop these packets so that any responses, if there are any, are very likely coming from a firewall that didn't bother to verify the checksum. There are two other ways we might be able to evade firewalls. One is to use the fragmentation fields in the IP header. The physical layer imposes a restriction on the maximum size of a packet or transmission unit that can pass across it. For example, it might be 1,000 bytes. The IP layer is responsible for splitting a data stream, which may be megabytes of data, into appropriate chunks for transmission over the network. When a datagram is subject to fragmentation, the ID field in the IP header identifies the fragment with a unique identifier or number. The more fragments flag is turned on, and the fragment offset field is set to indicate the relative position of the data chunk within the overall datagram. Fragmentation helps evade firewalls because performing defragmentation is a performance hit, so firewalls will often pass the fragments uninspected through to the target. Fragmentation is most effective when we choose a fragment size that splits the TCP header into different packets. The Nmap options that enable and control fragmentation are the -F option, which requests a fragment size of 8 bytes. Using the -F option twice requests 16-byte fragments. And lastly, there's the --MTU, or maximum transmission unit option, where the user defines the size of the fragments. Here's a couple of examples using these options. Note that fragments must be specified in multiples of 8 bytes, and since the TCP header is only 20 bytes long, a single -F is the preferred and most useful option. Here's a set of headers for a typical TCP/IP packet. Using a single -F option, the header would be split into 3 sections, like this. The first packet to be sent would include the first fragment. The ID field in the IP header is set to 23087, which uniquely identifies the datagram and will be the same for all 3 fragments. The more fragments flag is set to on, and the fragment offset field is set to 0, since this is the first fragment of the series. Note that the first 8 bytes of the TCP header are included with the packet. The second packet to be sent will look like this. The ID field is the same as in the first packet. The more fragments flag is set, since this isn't the last packet, and the packet offset field is set to 8, indicating that the data portion of this packet starts with the 8th byte of data from the datagram. Now the fragment data contains the second 2 lines of information from the TCP header. The last packet sent will look like this. Again, the ID field is constant. This time the more fragments flag is set to off, which tells the recipient that this is the last fragment in the series, and the offset field is set to 16, indicating that the data in the packet starts at byte 16 in the original datagram. The data contains the remainder of the TCP header. When attempting to use fragmentation, there are two potential issues that you need to be aware of. First, not all systems allow sourcing highly fragmented packets, and they will defragment the outgoing packets before sending them out. The Linux IP tables connection tracking module is one such system. If this is a problem on your Nmap testing system, one way to try and bypass source defragmentation is by forcing Nmap to use raw Ethernet frames. The other issue is that some firewalls queue incoming fragments and perform reassembly before forwarding them on to their destination. This, of course, defeats our reasons for using fragmentation, but isn't something that is easily detected or avoided. The other means of trying to evade a firewall is referred to as an idle scan. This scan uses the fact that some systems use a monotonically increasing ID field for each datagram sent out from that host. If we can find an idle system that isn't using or incrementing the ID field, and that system uniformly increments subsequent ID values, we can use that system to perform a scan that completely hides our identity. Very sneaky indeed. Here's the way this scan works. Suppose we've identified a printer as being idle and having monotonically increasing IP ID values. We start by sending a packet to the idle system, which sends us a reply that includes the ID value which we note. We then spoof a SYN packet to the target system using the idle system's IP address. Since the port is open, this packet elicits a SYNAC response from the target to the idle system, which, having no knowledge of the conversation, responds back to the target with a reset packet, which burns an ID number. We then send a second packet to the idle system, which again responds with a packet and another ID value. At this point, we've received two ID values from the idle system. If they differ by 2, as they do in this case, we can deduce that the idle system and the target exchanged packets and that the queried port is open on the target system from the perspective of the idle system. What if the queried port is closed? We start with the same query to the idle system and note the ID value in the response. Again, we spoof a packet to the target using the idle system's IP address. The target still responds to our spoof by sending a packet to the idle system, but this time, since the port is closed, the target sends a reset packet. The reset packet doesn't warrant a response from the idle system. We then query the idle system again and note the ID. Since the ID has only increased by 1, we can deduce that the idle system didn't respond to the target's packet and therefore conclude that the port is closed. Idle scans are sneaky and actually map the ports on the target from the perspective of the zombie and can therefore be used to map out trust relationships. For example, we might be able to map a network administrator's access to or through the firewall if we can find a time when their system is idle. The key to using this type of scan is finding an idle system. We'll talk more about that in the module on scripts, specifically the IP-ID SEQ script. An idle scan is enabled like this, where 192.168.5.4 is the idle system, and 192.168.23.88 is our target. Okay, enough about firewall evasion. Let's talk about other things that can frustrate our scanning. Let's talk about network address translation. Network address translation is a mechanism that remaps a multitude of internal addresses onto one single public IP address. Firewalls are often configured to perform network address translation to hide the IP addressing scheme on the internal network from the outside world. Furthermore, most organizations use private RFC 1918 addresses on the internal network and have a very small set of routable addresses on the outside of the firewall and the DMZ. When scanning from an internal workstation to an outside system, there is little to worry about since appropriate address translation happens transparently. However, if the situation is reversed, we find that scanning from an external network to an internal network with a NAT enabled is very restrictive. The only IP address we can see from the external side of the NATing device is the one configured on its external interface. We have no way to define that we want to pass through the firewall to a device on the internal network. So in this case, trying to scan 172.19.5.232 from outside the firewall will not work. Finally, let's discuss intrusion detection systems. A network intrusion detection system, or IDS, is a device that monitors network traffic for malicious activity and produces reports about policy violations, which are published to a management station. Network intrusion detection systems are placed at strategic points within the network to monitor traffic to and from all devices on the network. It works in promiscuous mode and performs analysis of passing traffic for the entire subnet. Once an attack is identified or abnormal behavior is sensed, an alert can be sent to a network administrator. An IDS can be configured to look for many signs of attack, including signatures, header anomalies, and packet rates. One way to avoid triggering an alert on an IDS due to an excessively high packet rate is to set a performance template sufficiently low to avoid detection. How low might need to be determined by testing using several expendable IP addresses. Other ways include making your traffic look as legitimate as possible. Two options that allow you to do that are the --source-port number and the --data-length option, which appends random data to a sent packet. These options could be used together in a host enumeration scan to make your traffic look like it was coming from a secure web server with an encrypted payload. We can also hide ourselves as the source of the probes. The -S option can be used to spoof a source IP address that isn't really ours. This can create some interesting traffic on the target, but since any replies will be routed to the spoofed address, it isn't really useful from an information gathering point of view unless we're performing an idle scan. There are legitimate uses for this option. For instance, we might have multiple addresses associated with one network card, or we might even have multiple network cards, in which case the -E option will be useful as well. Similarly, we can set a fictitious MAC address in the physical layer header to make it look like our card is from a different manufacturer. While this won't fool anyone for very long, it can deflect suspicion for a while. The argument to the --spoof-MAC option can be a full MAC address, a vendor's prefix, or the vendor's name. Here's a few examples. The last one sets the MAC address's first 3 bytes of data to match Cisco's prefix, and then the last 3 bytes of the MAC are by default set to random data. One last way we can hide our scans is to flood the IDS with misleading data. The -D option allows us to specify other addresses that should be used as decoys. The target host will see that it is being scanned from multiple hosts and won't know for sure which one is really initiating the probes and which ones are innocent. This example specifies that only 2 IP addresses be used as decoys, but in practice, if you really want to hide, you should list more. Use caution when using this option, since Nmap has to generate a complete set of probes for every decoy, which can significantly degrade the performance and speed of your scan. At the end of the port scanning phase, Nmap provides us a list of open ports, and it reports the service name from a simple lookup in the Nmap services file. This lookup is usually accurate, but could be misleading. People can and do run standard services on non-standard ports. Furthermore, when performing a security audit of your network, you really want to know which servers and which versions are running on those open ports. So in this case, we'd like to know more about the HTTP service running on port 8080. Is it IIS or Apache? Is it Apache version 2.2 or perhaps version 2.4? The Nmap version scanning subsystem obtains all of this data by connecting to open ports and interrogating them for further information using probes that the specific services understand. Not all versioning attempts will produce all of these outputs, but Nmap tries to determine the service protocol, such as FTP, Telnet, or HTTP, the application name, for example, Apache or IIS, the version number, 2.2 or 2.4, and the host name. These 4 attributes are determined using a database of probes that perform application-specific queries. 2 more fields that version detection can discover are device type and operating system. 2 additional techniques are used to discover these 2 attributes. One is application exclusivity. For example, if Microsoft Exchange is identified, we know the operating system is Windows, since Exchange doesn't run on anything else. The other technique is to query loose-lipped applications about the platform they're running on. Many will happily divulge information that can be used to deduce the underlying operating system. Versioning can also resolve some ambiguities that result from the port scanning phase. Some UDP and TCP ports are left in the open filtered state after a port scan is unable to determine whether the port is open or filtered. Version detection will try to elicit a response from these ports using pre-configured probes from a database and change the state to open if it succeeds. Version detection is enabled using the -s option. Optionally, you can include the --version-intensity option and specify one of 10 intensity levels. The default is level 7. The --version-light is an alias for an intensity of 2, and the --version-all is an alias for an intensity setting of 9. The default is usually sufficient. Okay, demo time. Let's look at a couple of version detection commands. First, let's run a basic Nmap command against my default router. Alright, there's nothing new here. We've seen all this before. What I wanted from the output is to note the time it took to complete the command. In this case, it took 1.84 seconds. Now let's rerun the command, but this time add the -sv option to perform version detection. Okay, I've clipped the recording so you didn't have to wait for the command to complete. But note the time that it took to run this version of the command. 163.99 seconds. That's a huge difference from the base command without the versioning. Versioning can be very, very useful, but it should be used judiciously. Alright, let's talk about the output. The option has added another column to the results table which lists the detected application and, where possible, the version number. On port 80, it was able to determine the application as light HTTPD and that it's using version 1.4.28. Let's take a look at another command. This one is going to perform version detection on port 8080 of my printer. Nmap was able to determine the brand and model of my printer, and the results are output in the results table. But in this case, it was also able to perform device type and OS family identification through other means. The results are presented in the service info line, where Nmap found the common platform enumeration, CPE representation of the hardware. This information, when available, can be more reliable than the OS detection we're going to discuss in the next section. Let's look at one more command. This one is going to scan port 2022 on one of my laptops. One of the challenges of performing a network security audit is identifying all the non-standard stuff. While the standard port for SSH is port 22, people can and do run it on other ports. Finding port 2022 open on our target system is informative, but being able to identify the application as SSH is even more useful. In this case, Nmap's versioning phase has identified the service as SSH protocol version 2.0, but can't determine the specific application implementation. In such cases, it provides you with the information that it retrieved and asks that the fingerprint be submitted for inclusion in its database. From the fingerprint data, we can see that the remote system is running OpenSSH version 6.6. Version detection and OS detection work very well together. When you need specific details about a target system beyond just a list of open ports, it's likely that Nmap can provide those details using these two scan phases. While powerful and informative, these two phases have their limitations. Next, we're going to talk about the Nmap scripting engine, where boundaries are removed and our limits are expanded to vulnerability detection, exploitation, and beyond. Hi, my name is Kirk Marshall. In this module of Network Security Testing with Nmap, we'll be discussing the Nmap scripting engine. The Nmap scripting engine, or NSE, is a capability that allows Nmap to be extended using user-defined plugins, which are limited only by a programmer's creativity. Currently, there are 484 scripts in the NSE library. That's 4 more than when I began writing this course, so new ones are getting added all the time. The Nmap scripting engine is called in its default mode using the -s option, which runs all scripts in the default category that are appropriate for the target service. Alternatively, you can enable the scripting engine using the -- script argument and specify one or more scripts or script categories. A number of scripts require additional arguments, which are specified using the -- script -args option. Nmap has 15 script categories that can be used to call a similar set of scripts for a given service. While using categories might have a place, my preference is to specify desired scripts specifically on the command line. Since they can add significant time to the scan, I find that only executing the scripts I need saves time. The documentation for the NSE is found at this URL. With 484 scripts, there's no hope of knowing them all, so having the reference page bookmarked in your web browser is a good idea. I find I refer to this page frequently. You probably will too. Here are two basic examples of calling the scripting engine. The first performs all the scripts in the default category for the service running on port 80 on www.cnn.com. The second example executes the HTTP chrono script on the service running on port 80 of www.ibm.com. We're going to demonstrate several scripts later where we'll show more complex examples. Let's look at a couple of examples. This command is asking Nmap to perform versioning on port 1723, which is the point-to-point protocol on these two targets. As you can see in the output, Nmap was able to determine the version. In this case, all we specified was the -sv option, but the pptp-version script was called by Nmap in the background. In this command, we're scanning port 80 on the host www.abc.com, and we're asking Nmap to run two scripts against this target, the HTTP-header script and the HTTP-chrono script. The results from this command are typical for script output. In the report table, we see two entries, one for HTTP-chrono and the other for HTTP-headers, followed by the information that each of those scripts gathered. The HTTP-chrono script performs repeated gets of the website and prints out statistics, the average, the min, and the maximum times that it took to retrieve those pages. The HTTP-header script returns metadata about the web pages returned. Often the headers provide us additional information. In this case, we can see that the server on the remote target is the Apache web server. Here we have another example. In this command, we're asking Nmap to run the HTTP-email-harvest script against this target web server. This script spiders the web server looking for email addresses. Here in the output, we can see that the script found two email addresses. By default, this script sets parameters that limit the spidering to a depth of 3 links and a page count of 20 pages. These limits might be suitable for a small website, but when scanning a large site, they will prove to be too restrictive. These parameters can be changed using the -- script -args option like this. Here we've reset the max depth parameter to 9. All of the parameters that control a script's options, if there are any, can be set in a like manner. Each script has its own web page at nmap.org, which describes the various arguments that can be set to control it. From the output here, we can see that increasing the max depth option to 9 found several additional email addresses. Here's another example. We've referred to this command several times already. With this command, we've asked Nmap to execute the IP-ID seq script to evaluate the predictability of the target's IP-ID numbers. Recall that a system with predictable ID numbers can be used as the zombie in an idle scan. The results from this system came back showing that the remote system returns all zeros as the IP-ID sequence number. This one isn't going to work for us. Let's try another. This one came back and says that it's unknown. That's not going to work either. Let's try one more. Alright, with this last test, the results came back and indicate that this system indicates its IP-ID values incrementally. This system could be used as a zombie in an idle scan. Alright, let's run one more command, but before we do, let's look at two files that I've created on my testing system. The first is user.list, which simply contains a list of user accounts. The second is pass.list, which contains a list of passwords. So here's the command we're going to run. This command calls the telnet-brute script with the two arguments that identify the user and password list files. This script connects to the target system on port 23, which is Telnet, and tries to log in using every combination of username and password listed in the two files. Ah, look at that. We found one username and password combination that can successfully log in. So without further ado, let's get started. This system is connected to the internal network of a client. The first thing we need to do is find out what network we're on. Fortunately for us, the network is configured to use DHCP and our system is automatically assigned an IP address. The output here from the ifconfig command lets us know we're on the 192.168.25.0/24 network, which we can deduce from the inet adder and mask entries. The next thing we're going to do is find other systems on our network. This command uses the -SN flag to disable the port scanning phase. We'll get to port scanning in a moment, but right now we just want to run the host enumeration phase. I haven't specified any specific host enumeration options. Using the defaults are going to work just fine here. In fact, even if I had included any options, they most likely wouldn't have mattered, since host enumeration on a local network, one to which we're directly connected, is usually performed using the results of the address resolution protocol. Cool, so we found a bunch of systems. Let's rerun the scan and pull out just the IP addresses from the report using the awk command. Okay, there's the list. It looks like we found about a dozen. Let's save them to a file. I happen to know that the network we're on is at the client's data center. They also have several remote offices, and in a real audit, we'd want to test all of them, but we're only going to test one remote office to keep the scope of this demo to a reasonable size. I've selected one remote branch, which is using the 192.168.130.0/24 network to include in our test. Scanning that network reveals more hosts. Let's save them to the same file. Here's the list of all IP addresses we've identified on both networks. Since all of the hosts on each subnet are going to use the same route, we only need to run one traceroute to each network. Running traceroute against a system on our local network shows that we're directly connected to that system with no routers in between us. Let's see what the route looks like to the remote branch. Wow, okay, this looks a bit more interesting. The remote branch is 7 hops away from us. We recognize the first and 7th IP addresses as belonging to our local network in the remote branch. The 2nd and 6th are both 10.254 networks. Since the IP addresses are the same on both of these networks, they are most likely managed by the same network management team. In this case, I'm guessing that they're managed by our client. The 3rd, 4th, and 5th hops also have similar IP addresses, 198.18, and are most likely systems within the MPLS cloud of the telecom provider. These are just guesses, but I'd bet a cheap lunch that I'm right. Let's move on. The next task we should perform is identifying open ports on the live hosts we've discovered. Let's run a half-open scan and look for the top 1,000 TCP ports. Here I've asked Nmap to scan the hosts listed in the ip.lst file and write the results to the ports.tcp file. Using files to save the results from each phase of testing allows you to refer back to them and call them again repeatedly. Alright, let's do the same for UDP ports. I've chopped the waiting time out of the video so that it looks like it ran much faster than it did. Here you can see that the UDP scan took 30 minutes to run. At this point, we've got 3 files, a list of live systems, a list of active TCP ports, and a list of open UDP ports. Now the real work begins. By visually scanning through these files, we need to identify systems and services of interest, and then use the versioning and scripting capabilities of Nmap to investigate and identify the services running on them. In looking through the ports.tcp file, I noticed a number of systems that looked like this one, which appear to be a standardized workstation with VNC installed for remote administration and help desk functions. But I also noticed this one, which is different from the rest since it doesn't have the same set of ports. Let's investigate this system and see what we can find. Let's start by running versioning and OS detection on it. I've included in the list of ports the 4 open ports and 8081, which we hope is closed to help with the OS detection. In the output, we can see that it's running SSL on both port 80 and 443, which is a bit strange, and that it wasn't able to identify the service on port 8080. The OS detection returned a number of guesses of Linux, but didn't find an exact match. Let's see what else we can find out. Perhaps the HTTP headers on port 80 will give us some indication of the type of system we're testing here. No luck there. Let's try port 8080. Okay, those aren't much help either. Let's try the http-enum script. These directories might yield some information, but before we check them out, let's have a look at the http-title script. Okay, here's something we can look into. The title reports that the system is a March Networks command client. A quick internet search, and I found that March Networks supports video recording. This is probably a security camera system of some sort. We could keep working on this system and maybe learn more, but let's move on. Looking elsewhere, through the ports.lst file, I found a system with port 1433 open, which is a Microsoft SQL server. Let's see what we can find out about this installation. The output here shows that this system is running Microsoft SQL Server 2008 R2 and gives us an idea of the patching level. This is all valuable information. Let's see if we can find anything else out about it. Let's test it for empty passwords. In this case, we got back nothing, not even an indication that the script ran. When a script isn't able to query the remote system or provide any meaningful output, the default action is to provide nothing, like you see here. This keeps the output short and clean, but can make you wonder if it even ran. It did, it just didn't find anything. We're just getting started, and this process of looking through the ports.tcp and ports.udp files and then testing interesting targets can continue on as long as you feel there is additional benefit of proceeding. The steps we've performed here are the basis for continued investigation. Only the names of the scripts will change. Let's look at one last command. In this command, we're scanning port 1 through 1024 on www.cnn.com using the ACK scan. Recall that this scan allows us to map firewall rule sets. In this case, we're not really interested in cnn.com, but in the firewall guarding the network perimeter. We found that all 1024 ports are listed as unfiltered. We can interpret these results to mean that the firewall is not blocking outbound access at all. Any traffic on any port can pass from the internal network to the internet. While this is not the most secure configuration, it is very typical.